Okay, I guess we can start now. So welcome everyone to this seminar. So let me first introduce myself. So my name is Yahui Zhang. I'm going to be the co-organizer of this seminar series on high-TC superconductor. So I'm currently a postdoc in Harvard, working with Subir and Ashwin. So today we are honored to have Subir giving his second talk. So a few weeks ago, Subir gave his first talk on high-TC superconductor in the clean limit. In this talk today, I believe he will give a complementary perspective on a model with random interaction and make an interesting connection to SRK physics. So let's welcome Subir.
Okay, excuse me. Thank you very much, Yahui. Great to be back, and thank you all for coming back for the second installment. As Yahui mentioned, my previous talk was about a model, in fact, that's due to Yahui and its connection to the phase diagram of the cube rates. And today will be somewhat different work on the random system. There was a lot of discussion last time in my talk, and I hope there'll be a similar discussion today. If you wanted my previous talk, you can find the video online at the CMSA website. And of course, thanks to Juven and Yahui for organizing this series, and CMSA. I think we're going to have a very interesting semester with lots of talks. I think the next talk is experimental tomorrow by Ina Vishik.
Yes.
Okay. Right. Okay. So just a quick reminder. So I won't spend as much time as I did on my first talk on the general introduction. This talk is motivated by the cube-rate system, which is a square lattice of electrons hopping on a square lattice with one orbital per site, and then you vary the density. Then as you vary the density, there's this famous phase diagram as a function of the whole density away from half filling. Where at half filling you have an insulator. Then as you dope it at low temperatures, you get the high temperature superconductor. But my talk today is actually focused on the metallic states that appear above TC. So at low doping, we have the pseudogap metal. In intermediate, there's sometimes a region called the strange metal, and only at high enough doping do you get Fermi liquid. So we believe that, at least in the models I'm going to study, that the transition between the pseudogap metal and the Fermi liquid is the fundamental underlying transition between two distinct metallic states. And the superconductivity is some sort of instability that appears near the quantum critical point at PC. And so we really want to study this metallic transition. What is the nature of the transition between the underdoped metal and the overdoped metal? Of course, the overdoped metal is believed to be a conventional Fermi liquid. But then what is the nature of the pseudogap metal and what is the nature of the transition are really some of the key questions in the field. So I'm just going to show, of course, there are many, many experiments, and we're going to hear a lot more about them in this series. Just going to show 3 experiments, the same I showed last time, which characterize the difference between these two metals, between the P less than PC and the P greater than PC metal. So this is just as a reminder, this is an AD angle dependent magnetoresistance experiment from Brad Ramshaw and his group. And what they see after some analysis, which I won't review today, they conclude that very likely the underdoped metal has Fermi surfaces of the shape of these whole pockets, whereas the overdoped metal has a large Fermi surface. Now, this large Fermi surface is exactly what you expect from Fermi liquid theory, so things are in excellent shape here. And this Fermi surface is something you might expect in the presence of magnetic order, but it's also clear that there is no appreciable or significant magnetic order in these materials at these dopings. So that's one of the big puzzles. Why is the Fermi surface small and even without magnetic order? as they say, antiferromagnetism is not found at these dopings somehow, but the reconstruction associated with antiferromagnetism is still somehow happening. Another important characteristic, which will relate somewhat to the model I present today, is that there's appears to be a large peak in the specific heat. The temperature derivative of the specific heat is C over T near the critical doping, and also in transport measurement, a jump in the carrier density. And finally, and this will be most relevant to the disordered systems I'll talk today, there's also indication, at least in an applied magnetic field, of glassy behavior in the pseudo-gap regime at low temperatures, some kind of antiferromagnetic or spin glass. Okay, so that's a very lightning review of things I spent more time on last time. And as I mentioned already, the last time we talked about a model for the phase transition in a completely clean system. This is a model based on the idea of insular qubits due to Yahui, and you can hear more about it in the previous from the video. And today I'm going to talk about a random system. Basically, what we're going to do is we're going to take a simplified model where we assume that the electron can hop from any site to any site with a random hopping, and also has a random exchange between any pair of sites. So you could say, so we're going to study random and all-to-all couplings, and so a natural question is why? And I'll try to give you some motivation before I launch into a description of these models. You may not be convinced. Well, anyway, but I would say that in the history of physics, just understanding such simplified random models has certainly led to many, many interesting developments. And so, that's partly what motivated us. Maybe there will be similar new insights that we can gain from these random simplified models. So part of the motivations, though, if you're not yet convinced, the randomness is present in the real system, as we saw already in the presence of spin glass behavior. And the randomness will be actually fairly innocuous in the end. The final equations don't have any randomness in them. And that's because of the property of self-averaging. That even though the Hamiltonian is random, each site is coupled to so many other sites that every site is average. So the Green's function are the same on every site, with the exception of, on the spin glass phase, where certain correlators, of course, vary from site to site. The spin is pointing in different directions on different sites, but we won't be directly interested in those. Also, I think there's quite a lot of evidence from the experiments and from the phenomenology that this transition is primarily a kind of a quantum transition in the nature of the many-body wave function and its entanglement. And much like topological order and gap systems, like the transitions between two fractional quantum Hall states, for example, we still expect there to be a sharp transition even when you take a random system. Randomness doesn't smoothness or destroy out this transition. So let's just put it in there anyway, just to make sure you focus on the right physics, which is not associated with special symmetries. So this is kind of what I said. Introducing randomness removes the distractions of other order parameters. It doesn't get rid of all of them. It may introduce a new one, which is the spin glass order. But that's fine, because that's actually what's seen. All right. So as typically happens in these all-to-all problems or large dimension problems, in the end, the problem reduces to a single site problem or a quantum impurity problem. We have a single degree of freedom on that impurity site, coupled to some kind of self-consistent environment. And that's the type of problems that we are going to look at today. And I will say that even if you don't like this motivation of random systems, there's another set of models where you take the limits of large spatial dimension without randomness, where you get essentially very similar impurity problems in the context of what's called extended dynamical mean field theory. But here it turns out, but those models are, in some limit of large dimension, which is very hard to study in any other way. But if you think of them as random systems instead, then you have an exact representation of a Hamiltonian. And then you can solve that Hamiltonian numerically. So then you can compare your fancy theories and direct numerical analysis. And that's what we're going to, we started doing some of that. And hopefully it's only with this comparison that we'll finally have a complete theory, even of the simplified problem. All right, so with all that motivation, let me just now describe the model I'm going to study. So even if you're not a physicist, but a mathematician, formally, this completely defines the problem. This contains everything you need to know. So you have a Hamiltonian expressed in terms of the electron operator and the spin operator. The electron's anti-commute, and the spin is related to the electrons by this, where sigma are the Pauli matrices. Of course, what makes this problem very difficult is this constraint. You're never allowed to have more than 2 particles per site. And P is the whole density away from half-filling. So there are these couplings, Tij and Jij, and we just take them to have 0 mean and Gaussian random value. That's it. And then you take the large-n limit, and these are the 3 states on each site, okay, which are allowed by this constraint. And that's it. So this is, perfectly well-defined problem, and we'd love to know, hopefully, we can finally get an answer to what is the phase diagram of this model. I don't think we're far from the full answer, but that's the goal of my talk, is to figure out what is the phase diagram of this simplified model, even with Tij and Jij random. And one of the questions would be, does this very simple model have a phase transition as a function of P, which looks anything like what's seen in the experiments? Okay, so I hope to convince you with some of our results today that it's very likely that's indeed the case. Even this very simple model has the basic physics of this pseudo gap to Fermi liquid transition. Okay, so here I had some animation. Yes, Juven.
There is someone posed a question.
Yes, go ahead.
He said that is there a particle symmetry in the model?
No, only at P equals 0, but in general, no. Oh, but of course, the phase diagram for P positive and P negative are the same in that sense. But at a fixed value of P, there's no particle symmetry. If you do particle the operation, you map P2 minus P, this number P here. Okay.
I hope this answers the question. If you don't, if that doesn't, you can unmute yourself. Another question I have, just make sure, do we study this in infinite plane? Or do we study in periodic or other boundary conditions on some cores?
There are just n sites. There's no geometry here. There's no space. There are n sites.
Thanks.
And
sorry.
Every site is coupled to every other site. It's a fully connected graph. Every site is connected to every other site. That's all.
Great for that. Yeah, thanks.
Okay. All right, so here's a picture of it. I mean, just so you know, you see these are n sites here. They're coupled by T, and every one of the T's is a random number. And electrons can hop, and they can exchange spins with the J, and all of these are random numbers. Okay, so that's the problem. All right, so I'm going to begin by talking the P equals 0 case, which turns out to be closely connected to some of the physics of SYK models. And this models were looked at 25 years ago, but with all the recent progress in the SYK model, we may be able to understand much more about this model, and I'll describe some of that. And then we'll start to non-zero P, and eventually also show some very recent numerical results, which will compare with this theory. Okay, so this is the random J model. Now you do have particle hole symmetry. There's always 1 electron per site. And then they can have random exchange constants with each other. Okay. All right, so this and Jij is a random number. So this is the model we'd like to know more about. and also the model, as you know, in a few minutes, where the spin S is acting not just in SU2, but also in some general group SUM. So the spin S is an operator which belongs to SUM. And of course, so far we've been considering the case M equals 2, but it turns out to also be useful to look at the large M limit. Okay. All right, so this is the problem now. It's just a problem of spins in some representation interacting with random couplings. All right, so if you want to explicitly realize this model, it's useful to write the spin in terms of some fermions. Now, I haven't written these fermions as electrons, these are spin-ons. So because they only carry a spin, no charge, and they have this constraint that F dagger F is 1. So now, because of this constraint, rather than inequality, it's inequality. This theory has a gauge symmetry once you write it in terms of fermion. It has a U1 gauge symmetry because you can rotate the phase of phi on every site independently without changing the Hamiltonian. And all states are gauge invariant because they only have exactly this occupation number. You could also write it in terms of bosons. There's no problem with exactly the similar representation. Formally, these two problems are exact, but there'll be, let's see, one or the other representation will eventually become more useful to us when we solve this problem in some approximation. Okay. So how do you solve this sort of problem? Well, for all these general spin problems, in fact, the solution is very simple. So there's a standard technique where you just average, write down this as a path integral, you average over the Jij, and once you average over the Jij, every site becomes equivalent to every other site. And in fact, the problem reduces to a single site problem. So you basically have to look at just the path integral of a single spin. So for SU2, the spin is just executing paths on the unit sphere. For SUM, it would be executing some more complicated manifold. And there are two terms. One is the Berry phase term, which computes the area of this enclosed by the path and multiplies by spin a half by 1/2. And there's a corresponding Berry phase term for, or Wess-Zumino-Witten term for other groups also. So that's this term here. This is just what encodes the spin commutation relations. And then you have an interaction, which is a self-interaction between the spin at different times tau, between two different times here with some self-interaction Q. Okay, so the essence of the problem is that when you start from this Hamiltonian and do the average, so far I'm neglecting certain subtleties associated with the replica and so on. I'm only taking the replica diagonal terms. We can put the replica of diagonal terms in, but unless you're in the spin glass phase, none of that matters. You can just work with the replica diagonal components. Okay, so the final question is, what is this Q, this self-retarded interaction? Well, that is precisely just the spin-spin correlation function evaluated with this partition function. So you have to pick a Q, evaluate this partition function, compute this correlator, and then compute, so call that Q bar, and then Q must equals Q bar. That's the problem you have to solve, and it's completely equivalent to solving the original problem. All right, this problem is too difficult to solve. Nobody can really solve it. There are numerical works, and I'll show you some of the results numerically in a few minutes. But, hello. Okay, somebody needs to mute themselves. I will mute. Yeah, okay. Okay, so what we do is we say, okay, let's assume some Q. So it turns out you can show quite easily that any kind of exponential decay never has any solution to this kind of self-consistency unless you break a symmetry, which would happen in the spin glass phase. So really the only thing that could work is some power law at long times anyway. So let's assume some power law with some coefficient gamma. Okay, so now to begin with, we're going to ignore this condition and just solve this problem. So this is a separate problem where Q is just some power law. What are the spin correlations of this problem? So that turns out to be a problem that you can actually say quite a lot about. That's kind of what we did in these papers a while back. So you take a power law, and then what you do is you decouple this Q. You think of the Q as coming, much like the Kondo problem, as coming from some environment. And this simplest environment you can take is just a free relativistic Bose field in these spatial dimensions. So you have an environment which is a free Bose field, sort of like the Kondo problem. The environment is a Fermi surface. And this Bose field is coupled to this impurity spin with a coupling gamma, where gamma is that gamma over there. And you can just integrate out phi and easily see that this is, you just reproduce this partition function. So this is the same problem. Once you assume this is exactly the same problem. Okay. So now in this problem, so this is like sometimes called the Bose-Kondo problem. You have a spin coupled to a Bose environment, spin at the origin of this d-dimensional space. So phi a is the field at the Bose field of the environment at the origin, and spin S has the spin commutation relations. Okay, and then what is the spatial dimension D? Well, this alpha here has to equal D minus 1 for this connection to work. Okay. All right, so now, but when you write it this way, well, then you can do it. You can open your book on RG and work it out. So it turns out there's an epsilon expansion you can do, where epsilon is 2 minus alpha. And at one loop, you get a beta function for this coupling gamma, which is the Bose-Kondo coupling. Sorry, where did it go? Yeah, so this Bose-Kondo coupling gamma here, which is the same as the amplitude of Q. There's a beta function, and there's an attractive fixed point in at least 2 order epsilon. And so that's great. So you're getting a critical solution, which is always critical. It flows to this critical fixed point under the assumption that you haven't broken a symmetry. And then you can sit down and try to compute the spin correlation function at this point. So it turns out there you can prove something quite remarkable. You can actually compute the spin correlation function to all orders in gamma. Even without actually computing the beta function to all orders. There's a Ward identity that follows from the fact that there's only one renormalization here, the wave function renormalization, and that basically fixes the exponent of the spin operator. And it's ultimately connected to the fact that the coefficient of the Wess-Zwienow-Witten term is quantized. It cannot be renormalized. So there you concluded that this fixed point, this Q bar, which is the spin-spin correlation function in this theory, this Q bar here, decays with a different exponent that you started with. You started with an exponent alpha. This is an exponent 2 minus alpha. And this you can prove to all orders in gamma or epsilon. Okay. So now you want to equate 2 minus alpha to alpha here. Well, that's a very easy solution. Alpha must equal 1. And that also actually means epsilon equals 1. And therefore, spin-spin correlation functions at this critical point in this theory decay as 1 over tau. Okay, so that 1 over tau is going to play a crucial role in everything. That's something that's really characteristic of a lot of these critical points in these all-to-all coupling models. Okay, as I'm going to show in a minute now, there's another way of getting this by some large M limit, where you should think of this as the spin correlation function, the product of Green's function of 2 spin-ons, where the Green's function of the spin-on goes as 1 over square root of tau. Okay, so let me tell you a little bit about that. So we've so far found this critical point in this epsilon expansion, and from that we've been able to, compute one exponent. But we'd like to. It's still a strongly coupled fixed point at epsilon equals 1. But we can only compute things order by order in epsilon. And also the self-consistency condition that we've imposed, we only impose it at the level of at the very end of the calculation, just by equating the exponents. We'd like to do a theory which really helps us understand the self-consistent critical point on its own term in some sort of non-perturbative way. And one of the benefits of all the recent interest in what's now called the SYK model is that we made a lot of progress in that direction. So this fixed point that we found a long time ago is another example. That's some sort of conjecture, but there's a lot of evidence it's true, of exhibiting what's called SYK criticality. So the SYK model is a slightly different model, which you can solve to a much greater extent. And once you have that solvable model and everything you learn there, you then can argue also applies to this model that was of more interest to us. So let me just review what is the SYK model. This is a slightly different model where you have, again, fermions hopping on an n-site cluster, but the interactions now are highly non-local. They involve fermions at 4 different sites, and all of these UA, B, C, D, there's n to the 4th of these UA, B, C, D. In the previous model, they were only n squared Gij. Here there's n to the 4th couplings, and they're all random numbers. Okay, a priori, you wouldn't think that this model has anything to do with the previous model, but I'll argue it has a lot to do with it. So anyway, this model can be solved in the large n limit, and everything reduces to these 2 equations for the Green's function of the electron of the C operator. This is just the Dyson equation, and this is this equation graphically shown here. And these were the 2 equations that were originally written down by us in '93, but they were obtained for the previous model, the SY model, rather than the SYK model. But in a different approximation I'll mention in a minute. So anyway, so these are the SYK equations. And what I just said, if you start from the model, the J model, the random J model, and you write the spin operator in terms of spin-ons, but now you take your spin-ons and allow them to have M labels. So your group SUM. And now you take the large M limit. So you're taking the large M limit of the J model I just described for SUM. Then you get, and this is how we originally obtained them, exactly the same equations, which are also the exact solution of the SYK model. And so this is, this is the Green's function is 1 over square root of tau. You square it for the spin operator, you get the same 1 over tau, which is very comforting because we just proved to all orders in epsilon, you must get 1 over tau. And that's exactly what you get in this model too. Okay. Now, what we'd love to do, of course, is to do some kind of, as I already said, go beyond this kind of saddle point and look at all the corrections, what happened at finite temperature, what is the structure of the 1 over n or the 1 over m expansion. We're a long way from that. We're still working very hard on those questions. But for this model, we can do a lot of that. A lot of, especially string theories, have contributed an enormous amount of technology to understand the structure of the fluctuations about these saddle point equations. And we fully expect much of that, not all of it, but much of it to also apply to this model. So this whole class of models, I'll just now say obey SYK criticality, and let me just review what are some of the key properties of SYK criticality. So it's a model of many degrees of freedom with no spatial structure, only time. So what are some of the properties? One is that the ground state is critical, meaning it has power law correlations, but more importantly, there are no quasi-particle excitations. You can't build up the many particle state just by combining simpler states. So in formal field theory language, you would say that there's really an infinite number of primary operators. And in fact, in this case, they all have, we now know, irrational scaling dimensions. Okay, but one of the key properties that was pointed out by Katev is that the critical theory with this, in principle, should have been apparent to us also in the early days, as an emergent time reparameterization symmetry. That is, invariant under tau goes to f of tau. If we just rephrase, this is sort of like the kind of thing you do in theory of general relativity. And in fact, what you end up doing is write tau equals tau plus epsilon of tau. You take small variations and you write down some effective theory for epsilon of tau. And that turns out to be very, very useful and tells you a lot what this epsilon, the theory for the epsilon of tau. Okay. So one of the properties of this model, which actually was understood in this paper with George and Parcolet, was that it has a large entropy at low temperatures. So the precise statement is if you take the n goes to infinity limit first and take the entropy per particle and then takes the t goes to 0 limit, that's non-zero. So the zero temperature entropy is non-zero because that's taking the t goes to 0 limit. But important to keep in mind that this is not the same as an exponentially large ground state degeneracy, as would be the case for classical models like with Pauling ice entropy. What it really reflects is that the many body level spacing is very small, even down to the ground state, as it's not the case in system with quasi-particles. Okay, and so there's a very large entropy near the critical point, which will also be important for many other things. And many of the properties at finite temperature and all equilibrium and non-equilibrium properties have this Planckian time or universal scaling, which is independent of all the couplings when just determined by the temperature. So that's similar to many strongly coupled systems in finite dimensions. But this is really the first solvable example of such a system, which also is compressible, that you can vary the density arbitrarily, and you don't have to be some commensurate relativistic theory to get this universal scaling. Okay, so I already mentioned about this time representation soft mode, and it turns out the effective action for this f of tau is what's called the Schwarzenegger. Okay, this sounds like fancy stuff to condense matter theorists, and you would claim, why should I care about all of this? Well, just roughly speaking, you could think of this as some mode representing thermal or energy fluctuations. And as a consequence, these fluctuations contribute to the specific heat. So that's the connection with energy. So it turns out this model has a linear and t-specific heat, just like a Fermi liquid, but with the coefficient gamma. And this gamma comes from these time reparameterization fluctuations. So it's very different from the usual origin of linear and t-specific heat, where you have free fermions around the Fermi surface. Here it's time reparameterization fluctuations. Of course, in a Fermi liquid, S0 of Q is 0. Here, this is non-zero. And that's something we had understood earlier. This was understood by these people, the second term. Okay, and I guess I've already said these correlations decay as 1 over tau, and I've already given you the argument why this is robust to all orders based upon our earlier considerations. Okay, so what we can do now is look at corrections and the temperature dependence to this. So this is at 0 temperature and to leading order. So we can now do much better with all the stuff we learned from SYK. We can go to finite temperature, and we can also get the second term. So one example of this, which was already in these papers, is for the SYK model, the corresponding statement would be you look at the correlation function for the spin-ons. In that case, it has an exponent 1/2. At finite temperature, you get this form from conformal invariance. That was understood by George and Parcolet already. And then you have these corrections coming from irrelevant operators. And the dominant irrelevant operator, which also gave the leading correction to the entropy, is this time reparameterization mode for this model. And that gives you a correction that's linear in temperature or linear in frequency, depending on which regime you're looking at. So there's some scaling function here which in principle can be computed. The only unknown here is alpha G, but this alpha G is related, in fact, to the gamma. Okay, so we started examining these predictions more carefully for this random J model, and there's been some very nice work which is not yet written up with a lot of numerics and analytics on all kinds of such corrections by Maria Tikhanovskaya and Hao Guo, two students at Harvard, and Grisha Tarnopolsky, who's a postdoc at Harvard, going next year to Carnegie Mellon. Okay. All right. So what can we say? So let's measure it in terms of things you might measure neutron scattering if you had some kind of random spin system. Let's measure the local dynamic spin susceptibility. Well, the Fourier transform of d tau over tau gives you a log, but when you take the imaginary part, that just gives you a step function at the origin. And at finite temperature, that step function becomes this tanh. Okay, so this is a function that it becomes a step function as t goes to 0. So the imaginary part of susceptibility, which has to be an odd function of omega, has a discontinuity at omega equals 0 at t equals 0. But what we can do is actually now even measure the correction, compute the correction, and this is the numerical computation, and it fits this form extremely well. We can only do the numerics in this case at 0 temperature, so it's linear in omega as shown here, and this coefficient alpha sub s is related to gamma, and you can compute in the large M limit anyway what this number is. So we have these corrections to the susceptibility. So this thing, of course, at negative, this is at t equals 0. So if you go to negative omega, it's going to have a discontinuity. Whoops. And that should be below 0. Whoops. And at finite temperature, it gets smoothed out over a temperature scale T, like that. Okay. All right. So I'm focusing a lot on this correction because it'll turn out that it is precisely this correction here from the Schwarzenegger that will be important for the transport properties once we dope the system. Okay, so now I also want to talk about some recent work by Henry, Shackleton, and others, and I'll show that work in more detail later when we get to the doped system. But in this case, this work is reproducing earlier work by Arachia and Rosenberg. So what they did was just take an exact diagonalization of the J model for her SU2. And in that model, after averaging over many sites over some cluster of, 20, 30 spins, you can compute chi of omega. So the blue line here is the result from exact diagonalization. So the first thing, I would like you to notice that this shape of chi of omega in this finite system, it's not too far from this function that you got in the large M limit. And in fact, here's the large M theory rescaled in some reasonable way to match this linear slope here. And it's not too bad. We don't quite understand the reason for this bump here. It may be because of some finite size effects and commensurability effect with finite systems. But however, it's not too bad. But the most noticeable thing, however, is this bump here. So this seems to be an extra spectral weight at low frequencies compared to the large M limit. And that is in fact believed to be, as claimed by Arachia and Rosenberg, to be the presence of spin glass order. So if you just take this little spectral weight and compute an Edwards-Anderson order parameter, you get a very small value of around 0.01. But that's not as small as it seems, because the order parameter is the square of the spin, and the maximum moment is 1/2. So the Sharrington-Kirkpatrick model would have a moment of 1/2 at t equals 0. So you have to rescale by a factor of 2 and take the square root, and that gives you something that's 20% of the classical moment. For reference, the square lattice antiferromagnet has a moment that's 60% of the classical moment. So 20% is quite a small number, but it's clearly visible here. So there is spin glass order, but at higher frequencies, it seems to match this SYK-like frequency dependence quite well. Okay. All right, so that's all I have to say about SYK physics in its simplest form and this random antiferromagnet. Are there any questions? And now I'm going to apply the same insights to the doped system. But the basic ideas are all here. Yeah.
Can I ask a question?
Yes, please.
This reparametrization symmetry, is it true for all models with 1/tau correlation functions, or is it something specific to the SYK model?
Well, I believe it, so any zero-dimensional critical point of this type.
By zero-dimensional, you mean anything which has spatially local correlation functions, but the time correlations are as 1/tau. Is that what you mean? Even if it were not to be at the outset a local model or impurity model.
Well, so for example, so let me say if I take a multi-channel Kondo problem or the two impurity Kondo problem critical point, it's not those models do not have a time reparameterization symmetry. So what happens there? You have some critical state, say like at the critical point of a multi-channel Kondo problem. That has power law correlations and all kinds of things. But it's because of an impurity coupled to some other degrees of freedom. It's an impurity coupled to some Fermi surface with many channels. And that so the environment is also has its own conformal invariant, and this is sitting at the boundary of this conformal theory. I mean, that's the point of view Affleck and Ludwig took. So all of the models solved by Affleck and Ludwig do not have this time reparameterization symmetry. So the key to the time reparameterization symmetry is not only that you have a critical point, but also that the critical point, it's this self-consistency condition. That's crucial. There is no other power law source other than the self-consistency itself. So this self-consistency condition is the key to the time reparameterization symmetry. Because then you see that the action that you write down doesn't have any external power laws. If you integrate out the environment in a Kondo problem, you get a 1/tau to the alpha long-range interaction between in your impurity model. Once you do that, you've lost your time reparameterization symmetry. So in this case, you're in some sense, Q is itself kind of like a dynamical variable, and that's why there is no explicit time dependence in anything, even when you reduce it to a zero-dimensional problem. And that's the key to the time reparameterization symmetry.
So when you will introduce your the kinetic energy for the fermions in the problem, would you lose this similarly?
If that term, yes. Well, the kinetic energy, yes.
The T's.
Yes, you would.
T term.
The spatial gradient, yeah. Well, I mean, there is a term here for this model, for example. I don't think I've written it out, but there is the analog of there's this I omega term. This I omega, which comes from the, basically the F dagger df, from F dagger df d tau in the action. This gives you the I omega here. And this does break time reparameterization symmetry. This is why, this is why I said it's only at low energies and it's an emergent symmetry. But this term turns out to be totally irrelevant. It plays no role in the critical theory, although it does play some role in the structure, a minor role in the structure of the Schwarzenegger effective action. So that's the key. But if you had a term, like suppose I was doing a Kondo problem and in some environment, and then I added a term here where by hand, I said, oh, well, I have some environment, and the environment, when I integrate out the environment, gives me a term S of tau dot S of tau prime over tau minus tau prime to some exponent A, which is coming from the environment. that breaks the time. And this term is actually crucial to the structure of the multi-channel Kondo problem, if you think about it this way. That will not have the time parameterization symmetry and won't have all these features like the linear and omega correction and the linear and T correction to the entropy and so on. I mean, as you know, the entropy specific heat of these multi-channel Kondo problem have all kinds of powers, which are not always linear. So all of these problems, because of the self-consistency, only give you linear and T temperature dependence. So the key difference from all the things we have learned from Kondo problems is the self-consistency condition makes a huge difference. And we have, with all these amazing contributions from the string theory community, we've learned a lot on how to deal with that in a systematic way. Other questions? That was great.
Can I ask, how do you know that
going backwards?
The equation is well posed? Do you think there could be multiple solutions to it?
You certainly don't know that. Certainly that, when we wrote the SY paper in '93, we were sitting on it for 6 months, precisely because I wasn't sure that this solution that we found had anything to do with the real physics of this model. We don't know that. I would say that that's also true for the SYK model. We don't know that this solution is the right one. But for the SYK model, now there's numerical studies which leave no doubt that this is the correct solution. And for this SY or random J model, we're not 100% sure yet, but I would say that, I'm pretty excited to see how well this numerics is getting close to this solution. So this is some evidence that, yes, we've got the right solution. Of course, for large M anyway, and for small m, there's a spin glass order parameter, which we're now going to try to destroy by doping the system.
Thanks.
Okay. All right. So now we're just going to apply the same idea to a TJ model. Okay. So sorry, this is work done with Darshan Joshi, who's a postdoc in Harvard, Chen-Yuan Lee, who's a student at Harvard, and Grisha, you've already seen, and Antoine George at Flatiron.
Hi,
Okay,
Subir.
so this is the random. Yes.
Subir, there is a question in the chat by Gang Chen. So the question is whether the pure spin model has a random singlet phase.
Has a what?
A random singlet phase.
You can think of it that way. You can think of this solution, this SYK solution. Then I don't know. I don't see my chat. 1 second. Yes, it's in. Where's the chat?
Yeah. So
Go
so this is just making an analog with one dimension. So in one dimension, because of this result by Daniel Fisher, so any kind of randomness Heisenberg model will have this random singlet phase. So in 2 dimension, there is no exact solution, but some kind of argument by Patrick and others on a high dimension too. So I'm wondering if you don't have this, hopping term, just pure spin model, do you have this, random singlet phase, and can this state survive to some extent in the presence of, hopping?
Well, so right. So that's a good question. So the question here is, if you take the same model, but you take spins along a line rather than in this fully connected cluster, then you get what's called the random singlet phase, which is also gapless. But the physics of and this here also, we've got some gapless state, which is on a similar looking model. I would say, there's some partial resemblance, but they're really very different. The random singlet phase has to do with rare regions, and the gapless excitations come from rarer and rarer regions. And the spin fluctuations at all scales are decoupled from each other. You can just think of it as a bunch of independent singlets at some energy scale. So it's all a physics of extreme randomness where there is no self-averaging. This is like the opposite limit, where there's complete self-averaging. Every site is the same. The low energy excitations are not coming from rare regions. They're coming from all the sites. There's some kind of chaotic soup of all the spins, all these low energy excitations, and there's many, many of them. So, and it's got all these other properties. So I think there's some superficial similarity, but the physics is entirely different.
Thanks.
Okay. So this is the physics of quantum chaos, many body quantum chaos. That's the physics of and no quasi-particles. That's the random singlet phase is the physics of rare regions, which effectively there are quasi-particles. The quasi-particle just the singlet triplet excitations, which are all independent of each other. So there is some kind of you get a quasi-particle with the wide distribution of energies. Here, there's no such thing. Okay. All right, great, wonderful questions. So now let's go to the dope model by these people. So here you have 3 states per site, empty, spin up, or spin down. And you have now random T's also in addition to random J's. Incidentally, as I already mentioned, there are other models which have the same physics. You need not make T random. You can just put the model in a high dimensional lattice. And Jij in a high dimensional lattice need only be nearest neighbor. You get the same equations, but I prefer the random model because you can actually put it on a computer and check it other ways. Okay, so now you have 3 sites, like I said. And now we're going to think of to transfer all the technology from the random J model. We're going to think of these 3 states as the states of a superspin. Super because one of them is going to be fermionic with respect to the other. In particular, previously I'd said, for example, that let's just think of the spin up and spin down as 2 spin-ons being added to a vacuum, spin on up and spin on down. So in that case, let's think of the empty site as a holon, which is a boson being acting on the vacuum. So now, instead of having the constraint F dagger F equals 1, you have the constraint F dagger F plus B dagger B equals 1. You still have a U1 gauge invariance. And now you also see why I can think of the electron operator and the spin operator in exactly the same terms, because they're both bilinears in terms of these these fractionalized operators. So they both look like super spin operator. This is the usual spin operator, and this is a spin operator in a fermionic direction. That's what the electron operator is. And in fact, it's in the group, whoops, I should have written that here, SU1 bar 2. So meaning one direction is bosonic, which was the, which was this boson here, and these are the 2 fermionic directions. So this thing here is a superspin in the group SU. Oh, it's written down here, sorry. I've written right down there. Okay, SU1 bar 2. And the rotations in the SU1 bar 2 space. Okay, but we know that we can represent the spin with bosons rather than fermions, in which case the empty states has to be a fermionic holon. And now this is a rotation in the SU2 bar 1 space. But these 2 groups are the same. This is something we all know from having worked with these slave particle representations. The more formal way of saying it in mathematics would be that these 2 groups are identical to each other. These 2 supergroups. So here there's 2 fermions and 1 boson. Here there's 1 boson and 2 fermions. Sorry, 2 bosons and 1 fermion. Okay, you always write the boson first. All right, so now you average over T and J, and you know the routine. When you average over T and J, you get a single site problem. Now it's a single site problem for superspin, not an ordinary spin, because of this fermionic nature, but there's some self-interaction of the superspin, and there's a very phase term of the superspin. Okay, you can write it out in components, and then it'll look much more familiar to you, and you can see that in here. But there is an important difference now from the J model, there's also a chemical potential term, an S0, or a Zeeman field term, sorry, which acts linearly on the superspin. And this basically means that the energies of the hold-on and the spin-on states are not the same. And that's simply like a chemical potential. So as you vary it, you'll vary the density of hold-ons and hence the density of electrons. So there's a linear term that we have to worry about that we didn't have to worry about in the previous analysis. Anyway, so now you can do an RG analysis. Now you have two coupling constants. Instead of the one coupling constant gamma you had before, you have a chemical potential, which you have to worry about its flow. And then you do find a critical point. So this is just representing schematically. You can see more details in this paper. So now it turns out there's a critical point where the T and the J coupling, just like the gamma couplings, flow to a fixed point. This is a fixed point of the critical superspin. But this chemical potential, which is the difference in energy between the hold-on and spin-on states, is a relevant perturbation. So it flows off in this direction or that direction. So you have to tune something here. So for the J model, you didn't have to tune anything. It seemed to be, provided you didn't get spin glass order for large enough M, to just always be critical. This one requires you to tune a coupling because you don't have the full supersymmetry. There is a Zeeman term that breaks the supersymmetry, and that's a relevant perturbation. There are also other terms that break the supersymmetry, but that's a different issue. Okay. Anyway, so you have to tune something, and what you have to tune is density. So we would say, oh, this looks great. You have to find a critical doping where you'll be at this fixed point. So what is this fixed point? Well, the fixed point is where the spin-on and the hold-on states have the same energy, which means these three are exactly the same. And this means that, if these three states have the same energy, the density of holes is 1/3 because there are three states and one of them is a hole. And so the density of electron, the P value would be just 1/3. So this state has P equals 1/3. But this is to leading order in this epsilon expansion that we also do here. On the other hand, here, where S is less than 0, the spin-ons will be lower in energy. And here, where S is greater than 0, the hold-ons would be lower in energy. And we can compute all kinds of things at this critical point. And from that, I can now draw this phase diagram. Oops, sorry, before I get there. So at this critical point, I can compute the spin correlation functions. So I showed you for the J model, for the spin operator, this goes as 1/tau from this Witten type argument. The same argument here shows you that this also goes as 1/tau. The electron operator also is 1/tau because the electron is also a spin. It's a gauge invariant spin operator in the superspace. So they both decay as 1/tau. And this is rather bizarre. If you had a Fermi liquid, you would have this going as 1/tau, but the spins would go as 1/tau squared. So how do you understand both the electron operator and the spin operator is going 1/tau? Well, the only way to understand this is from fractionalization. So this model, even though you didn't put it in by hand, seems to tell you that there is fractionalization at the critical point, where the electron is a product of spin-on and hold-ons. The spin is the product of spin-ons, two spin-ons, and all of these fractionalized particles decay as 1/√tau, and then you can understand this. And that's exactly what happens in the large M limit, which I won't describe, but it's very similar to the fermionic large M limit. So to summarize, as a function of P then, there's a critical doping where you have the spins decaying as 1/tau and the electrons also decaying as 1/tau with density approximately 1/3 to 0th order. There'll be corrections to that. And then what happens? Well, at higher doping, here the hold-on states are lower, here the spin-on states are lower. Okay, so what is this state? Well, this is kind of easy. You want a Fermi liquid here, and that makes complete sense, really. The way you should think about it is that you want to take the lower energy state in any approximate theory. You want to think of the low energy state as being the boson, because that's good for your energy if you just do a simple mean field theory. So the simplest mean field here would you make this a boson and condense it. Well, if you condense the holons, then these F becomes the electrons, and you break the U1 symmetry, and this is in fact the density of these F is the density of electrons, and therefore this is just exactly a Fermi liquid. It's a disordered Fermi liquid, and then you can see easily that the spin correlation now decays 1 over tau squared, whereas this decays 1 over tau. Okay, but what about on this side? Well, on this side, what you should do by this logic, now these states are becoming very low in energy. So it's always preferable to make the low energy guys a boson. So you make this the boson and that the fermion. Now the boson carries spin. This is the SU21 theory. So when these bosons condense, you're going to get a spin glass state, which is in fact what we saw already happened at P equals 0, very weak spin glass order. So the spin correlation focus decay at time to a constant. It's still a Fermi liquid because these guys are moving around as fermions. There's some density of them. But the density of these is the density of holes, which is density P. So there's a lower density of these fermions moving around. So there's some kind of metallic spin glass with low carrier density. So that's all. So that means there's a phase here in this. This is the proposed pseudo-gap phase of this model, which has spin glass order and also has a low carrier density. Whereas here it's a disordered Fermi liquid with no broken symmetry and a high carrier density. And also at this point, you have the 0 temperature entropy, whereas on this side and this side, because these are Fermi liquids, you don't. So there's some maximum in the entropy right near the critical point. Okay, so, and then some ways the most interesting thing here, what about transport? So you can compute transport here and here relatively easily. Here you would conclude it's just a disordered Fermi liquid with carrier density 1 plus P with resistivity going as T squared. It's in this infinite dimension, you don't get to these Altshuler-Aronoff corrections, which will give you T to the 3/2 over here. And this is also a disordered Fermi liquid of some type, but the carrier density is small. But what about at this critical point? So this is a calculation we recently did in this large dimension limit so that we have a sense of space. And what you find in that limit is that, this Fermi liquid-like disordered Fermi liquid behavior of the electron correlations means that there's a residual resistivity which is non-zero. That doesn't mean it's a Fermi liquid because the spin correlations decay as 1 over tau. And as we showed, the resistance doesn't increase as T squared. So what contributes to resistivity? Well, to compute the resistivity, what you need, just like we considered for the spin susceptibility, is the subleading correction to this 1 over tau. Okay, so this is work done by Hao Yugo and Yingfei Gu. So I already showed you this before. If you looked at the spin-on operator, it had this 1/2 exponent with some non-conformal corrections, which went linearly with temperature or frequency. Now, if you look at the electron operator, you lose the 1/2, it becomes 1, and this part gives you the residual resistivity. For the leading correction, and this is, again, a very general argument coming from this time reparamerization symmetry, has to be a linear function of temperature. And this is something you can compute. So from this, you can compute the resistivity, and this is what's in this paper. And at least from the time reparamerization mode, you get then a correction that's linear in temperature. So at least we have a model in which the resistivity as T goes to 0 has a linear in temperature corrections. I should say there's a certain caveat that will be discussed in this paper with Maria Tikhanovskaya et al. There are also many other operators in addition to the time reparamerization mode. And at least in the large M limit, which is the only limit we can solve for those other operators. I mean, this particular operator we know is present for all M just from general arguments. But these other operators have strange scaling dimensions, and some of them even have a scaling dimension h less than 2, in which case that you'll get subleading powers, something like square root of T instead. So we do find some of this, but we do find that this coefficient for those operators are extremely small. And we have no idea whether this works down to m equals 2 or not. Anyway, but that's a subtlety that we discussed in great detail in this paper. All right, so then to summarize, in the random TJ model, despite the simplicity of the model, it seems to really have a lot of encouraging signs. And there's a critical point, at least in these various expansions, where the electron Green's function is 1 over tau, and the spin correlate is also 1 over tau. And this fractionalization of this critical point, you can understand this is the square of 1 over square root of tau of spin-ons and holons. There is linear and T-resistivity, at least from the time retranslation mode. There's a change in the carrier density. And there's also large entropy near the critical point. And many of these features are connected to properties of black holes, but I certainly haven't said anything about that today. Okay. All right, so that's a summary of the theory for the random TJ model. In the remaining, okay, I have another 5 or 10 minutes. Is that okay, Yahui? All right. I want to show some of the recent numerical results on the same TJ model.
Subir, you have at least
compare them.
Subir, you have at least 20 more minutes.
Okay, thank you.
Yeah, well,
so maybe there's a good time to pause. Any questions on the TJ model, at least the analytic analysis that I presented so far?
Can I ask a very quick question?
Yes, Andre.
Yeah. About this linear and T-resistivity, is it still correction to Renault?
Yes. So in the large M limit anyway, it's we can only compute it in the regime where this is a small correction to the leading term.
And
we don't
is there
know how
any
to compute it
numerics
elsewhere.
that shows that it may go beyond the correction region?
Yes, I'm going to show that numerics in a minute, but that's not precisely for this model. But I'm going to show that. That's one of the next things I'm showing. Yes, but we would love to. We're hoping there will be numerics for this model for SU2. This is for the SUM model that we know. For the SUM model, it seems pretty clear that this correction is smaller than that. But for SU2, there is some numerical evidence from a different model where that's not the case. Yeah.
Question.
Any other question?
At criticality, do you have a specific heat going as T or T log T?
Specific, it goes as T, but that's really a small correction to the entropy. There's a zero temperature entropy at criticality in these models. But the specific heat doesn't care about the entropy. The specific heat, if you define specific heat as ds dt, that's just a constant. It's gamma. It's some number which is related to this alpha g, in fact.
So you don't have a log correction.
There's no log. There's no log in this model. No. Okay. All right. So let's now turn some numerics. So the numerics, just so I can fit everybody on the same picture, are done on a slightly more general model where you have both the T and the J, but I'm going to keep the Hubbard U finite and non-zero and non-random. So it's going to be positive and non-random. And the previous analysis that I presented so far was really UH going to infinity. That was the TJ model I've talked about so far. But now let's just draw a phase diagram. So in this model, there's also double occupancy of sites because U is not infinite. So we're going to phase diagram as a function of P and 1 over UH here. So the TJ model was down here at UH equals infinity or very large. But let's first focus on P equals 0 as a function of UH. So this is a different axis. So first of all, for very small UH, no problem. It's just a Fermi liquid. You know, there's even the filling makes no difference. When UH is very small, it's just fermions hopping around with some random interactions, which are easy to treat. Okay. what about at very large UH? Well, we've also talked about that. That's the pure J model. And that was the work of R.K. and Rosenberg, and we saw a weak spin glass order present there. And this is an insulator because now the single occupancy per site. So the simplest assumption is that in between there's a metal insulator transition. So that metal insulator transition has been studied in some very beautiful recent work by Chow, Wenzel, Parkole, George, and Una Kim. So this is done by solving these self-consistency equations that I showed you earlier in schematically for both the spin correlations and the electron Green's function using quantum Monte Carlo in the replica diagonal sector. And after quite a lot of hard work, they've been able to solve it, and that's the half filling helps. I mean, extending it to finite doping require, even in that method, there are sign problems, but let's see, I think there are going to be interesting results in that direction too. But anyway, so what they found, so they've studied this, indeed found that there were only two phases. There was a spin glass phase and a disordered Fermi liquid with a critical point in between them. And what they found, to me, this was really extremely exciting, and this is really part of the motivation for a lot of this work. This is before our work. They found that the spin correlations have this 1/tau decay that's so characteristic of SYK models or SY models. So here's the actual numerical evidence at the metal insulator transition. Okay, I won't go into details. And they also found that the spin glass order appeared to extend anyway. They didn't really have detailed results in the spin glass phase all the way up to the metallic point. And they computed the DC resistivity. And this is to answer your question, Andre. So they found linear anti-resistivity down to 0.01 of the bandwidth. So this is really extremely low temperatures. I mean, there's been a lot of works earlier with some indications of linear resistivity from various DMFT-like methods. Those are generally at much higher temperatures. This is down to extremely low temperatures. You see linear resistivity only at this critical point, and with a negligible residual resistivity. So at least here, there's some numerical evidence of very small residual resistivity, and most of it linear. But this regime is very much out of analytical control, at least by the methods I've talked about so far. Okay, so that's this critical point. So now we want to, of course, and I'll put the spin glass insulator all the way up to that point. Now we want to dope it. So at very high doping, again, we expect a disordered Fermi liquid. No surprise there, because it's just a dilute Fermi gas then. And therefore, the simplest scenario is that the spin glass boundary comes here. And that's consistent with the scenario presented so far, which is the TJ model that we've studied. And then I've argued that this critical point here is what we've been studying. Okay, so now we can try to do numerics here. So as I said, the method of Cha et al. Is quite hard to implement. Well, it will be implemented, I think, by the Flatiron group. But let's just try exact diagonalization. So this is work by Henry Shackleton. I mentioned his name earlier. He's a graduate student at Harvard. Alex Vitek is at Flatiron, and Antoine George also at Flatiron. So this is the same local spin susceptibility I showed you earlier. This is at P equals 0 at 0 doping. And this was the spin glass peak that you saw. And these are various, what we expect very generally, that if you have SYK physics, there'll be a linear omega term here. So in the paper of Rosenberg et al., they've taken a Gaussian fit, which we think is not well motivated. But if you take the linear omega term, then you would say it's only this region here above the linear fit, that's a spin glass order. So anyway, there's some ambiguity in how you estimate the spin glass moment associated with this little bump. Our procedure is somewhat different from Rosenberg and RH here. But what does happen when you increase the doping, and this is the new results, there is, in fact, a spin glass order disappears. Okay, this is already 0.01, whether this is not very significant, but around 1/3, maybe a bit above 1/3 if you, and above this, you don't have spin glass order at all. So there seems to be some critical point near 1/3 where the spin glass order disappears, and that's very much in accord with the very simple argument I gave for the 1/3 point. That's the point where the spin-on and the hole-on states have the same energy, and that's where you expect the critical point in these models, near there. Okay, so and this, of course, this incoherent contribution here, the finite omega seems to persist all the way up to the critical point. In fact, even looks better here. So that's really very nice. So there's some indirect evidence of this, fairly direct evidence, I would say, of SYK physics with time parameterization mode and discontinuity at zero frequency showing up in the numerics at this critical point. And that's a very robust prediction of the SYK physics, the linear and omega dependence and the discontinuity at zero frequency. As a reminder, in a Fermi liquid, this would just go to zero. It'd be linear omega this way. So the Fermi liquid would look like this. That's a Fermi liquid. And we do start seeing that at higher doping, but this very sharp, almost discontinuous period of low doping, followed by the linear omega dependence, is exactly what SYK physics predicts. Okay, so another thing that Henry and Alex have done is compute the entropy. So this is the entropy for various system sizes as a function of doping. Now, depending on the system size, we can only have certain rational values of doping because the system size is small. So there's a lot of different rational points here, but they average over, I think, many hundreds of samples. And certainly at very high temperatures, T of 100, the entropy has a maximum, again, at 1/3, exactly at 1/3 in this case, because that's where the most states available, which is, I think, closely related to the fact that the spin-on and hole-on states have the same chemical potential. Okay, so now what happens as you lower the temperature? So now we go to T equals 10, T equals 1, 0.1. Yeah, that's about as low as you can go. And so certainly what you see is that there is still a very nice maximum in the entropy, but at somewhat lower doping, 0.2 to 0.25. If you go even lower, well, it's hard to tell where it is. And that's, at least qualitatively, is what we wanted. We want a maximum in the entropy right near the critical point, because that's where the quantum chaos and the black hole physics of the SYK critical point will kick in. So another thing, this is very preliminary, that Alex has worked out, is try to extrapolate to the zero temperature limit in the following way. So you first extrapolate for each system, let's see, what is this? For each temperature, you extrapolate the value to n goes to infinity, and then you plot the extrapolated value here as a function of temperature. So what you find at zero doping, where you have a spin glass state, the entropy does go to zero. In fact, this is the entropy per site, and in the classical spin glass, despite the large degeneracy of states and replica symmetry breaking and all of that, the entropy per site does go to zero, even in the Parisi solution. So that's great. You're getting entropy going to zero here. And then you increase the doping, phi equals 1/6, the entropy is still going to zero, extrapolate to infinite size, but right at 1/4, okay, depending on how you do the extrapolation, in some extrapolation, you do seem to find a small non-zero zero temperature entropy. But if you do a slightly different extrapolation, it disappears. And once you go to higher doping, there's no sign of it. So anyway, there's some evidence, I would say, and not anything more than that, that even the entropy certainly has a maximum that we are pretty confident about. But whether it has a zero temperature entropy, we can't conclude, but they're promising signs, let's just say, at this point. Okay. All right, so that's basically the end of my talk. I've kind of filled out this phase diagram here. this was the numerical work of Cha et al. Then there was the numerical work of Archer and Rosenberg here. I've shown you now some of the numerical work by Henry and Alex, showing at somewhat different P, at least for these finite system sizes, a spin glass transition and also a maximum in the entropy, and also spectral functions that are highly consistent with this leading behavior and its subleading correction at the critical point. Okay. All right, so that's the end of my talk. So let me just unify then my two talks and stop talking. So in the first talk, I used a very different approach where this ancillar qubit approach with no disorder. And then we started talking about all these ghost Fermi surfaces at a critical point where the Fermi surface changed in size. So what are the common features? So the common features I would of these two models is, first of all, there's a change in carrier density from P to 1 plus P, and some sort of fractionalization, at least at the critical point, if not away from it in some models, is really the key to the critical point. So it's what you would call a deconfined or fractionalized critical point. And then you find a surprise. I mean, just if you look at it from a more historical context, you get much more entropy at the fixed point that you naively would have thought. In the SYK, it's the black hole entropy is huge. But even here in this ghost Fermi ancillar qubit model, there were these extra Fermi surfaces that nobody ordered, which gave you a lot more entropy. Of course, no zero temperature entropy, but still more entropy than you expected. And that seems to be, I think, I would say a common feature of many of these quantum critical points between metals involving fractionalization. Okay, thanks a lot. So happy to have more questions, and thanks for listening.
Yeah, please ask questions. Is there any question?
A question on the numerical result.
Yes.
So there was a pretty decent linear in T resistivity without a residual resistivity. That was, was that for the same model which also numerically gave ground state entropy?
That's a good question. No, the numeric model. So the numerics we have studied. Yeah, okay, maybe I should go back to, yeah, here it is. So the numerics is here so far. The linear resistivity of Cha et al. Is here at zero doping, but at the metal insulator transition. Now, entropy here has not been computed. Okay, hopefully it will be soon. Let's see. I'm pretty confident that you will find a zero temperature entropy here also.
The slope of the linear resistivity in the model, what has it been numerically related to some parameters in the model?
Yes, so we expect at least there's several things that go into that slope. One of the things that go into the slope is the gamma value, the gamma of the specific heat. But there are also some other factors now, which we haven't fully, but in the large M limit, we can compute all of those factors exactly, not for SE2. In which case,
what I specifically wanted to know was if you have a 1 over tau in the spin-spin correlation function, or some fluctuation for 1 over tau, and if they are coupled to fermions with minimal coupling, with a constant coupling constant, perturbatively it gives a linear resistivity. Just if you do perturbatively or
so that's of course
self-consistent
that's
perturbatively. And I wanted to know whether the slope that you get numerically is just that, because that would be related to gamma, which would be the coefficient of the 1 over tau, as well as to the coupling constant.
Okay, so thank you for reminding us, Chandra, of your which I should have mentioned earlier, very early work on the marginal Fermi liquid, where you had electrons scattered off some chi of omega with something like this tanh omega over t term, and the coefficient here. So what you're, I think, implying.
I wanted to know in the numerical result, not as an expansion in large N, but the numerical result. Could you relate that? How good is that?
I don't know the answer to that. I mean, they have the data, I guess, for both the spin correlation and the spin susceptibility. But let me tell you what I think the theory will say. So the theory is different. So there's some coefficient here. Whoops, what happened? Oh, gosh. Yeah, so there's a, whoops, yeah. Okay, so there's a coefficient here. Let me call it V for Varma. So there's the coefficient here. So you would say that the resistivity is the coefficient is proportional to the coefficient here. Now it turns out in these theories, there's another coefficient, which is this one. This comes from the Schwarzenegger. So our specific heat is in fact related to the Schwarzenegger, which is related to this slope here. So in these theories, the resistivity is related to this slope. It's the same operator that gives you the slope is what gives you the linear resistivity. So in that sense, it's different from the marginal Fermi liquid scenario. Yeah, so it's a difference. Yeah, and that hasn't been tested. I mean, but that is a significant prediction of this approach.
If I can ask one quick question about the same.
Here. Oh.
Yeah.
Yes.
In the formula which you presented from your calculations, rho naught was the overall factor for resistivity. So even the linear and T term still has the same overall factor rho naught.
It does, yes. Yeah, so I should have.
The numerics which you showed, apparently rho naught goes to 0, but the slope is still finite.
Yes, so this form is special to large M. Okay, so we don't know what happens for small m. There's an exact cancellation that seems to happen for small m, which we don't find at large m, and so we don't understand this. I would say there's still some mystery about this. Quite a bit of mystery. We would love to understand what happens to this at small m. Yeah.
Subir, I have a technical question. If you allow. So
sure.
in your old work on hi, how you doing? So in all your old work on quantum magnets, you had all this kind of generalizations to not only other groups but also other Young tableaus. So is this something like a useful knob in this kind of story?
Yeah. So what Ilya is referring to, between if we just look at the spins, yeah. So this is the fermionic spin-ons, which correspond to columnar Young tableau for SUM. Oh, sorry, not columnar. I should know this. I can sorry. Oops. I'm getting all confused here. Yeah. So it's not columnar tableau. It's the horizontal Young.
Yeah,
no,
even
it is
with
the columnar.
The bosons, just not for TJ, just for J.
It's the columnar. Oh, the bosons are okay. This is bosons. Bosons are horizontal. Okay, I don't know how to use this properly. Okay, so for the bosons you have columnar, and for fermions you have horizontal Young tableau, whatever it is. Okay, I'm saying that all wrong. So you can certainly put colors here to make the other rectangular Young tableau, and you can take the same large M limit. It won't change very much. You'll get essentially the same type of phases. In fact, here, unlike the clean antiferromagnets we studied, with Nick Reed long time back, there was a big difference between the phases that you got from the bosonic large M or the fermionic large M. Here, you get the same, qualitatively the same physics from either approach at this critical point. So there's like a democracy, which you can also see from this phase diagram, you know. Yeah, so this phase diagram here, you see on this side, you see we use bosonic spin-ons, and on this side we use fermionic spin-ons. And if you want to do the RG, we can do the RG in either approach, and we get the same answers. And that's because.
But for all kinds of orthogonal or symplectic, you would expect the same. It's like a Majorana physics instead of charged carriers, right? So you would have the same physics anyway. If you take,
could you just repeat that, Ilya?
Sorry, I'm saying if you go from SUN to SON or SPN, that would be like studying Majoranas instead of complex fermions. Would that change anything?
We haven't done that. But that could change things. Yeah, that would change the physics, I think. But that'd be a different problem with Majoranas. We have to have a density variable. We have to have a global conserved U1. That's important to dope it and to get all of this physics. So, and it's a U1 gauge theory in both cases. So Majorana, you might get Z2, and you're really talking about critical points in a superconductor and so on.
All right, thank you.
Sure.
Is there any question? So, if not,
thank
so
you all so much. I really enjoyed that.
Thank you, Subir.
Thank you, Subir.
Okay, bye-bye. And tomorrow, so tomorrow there's another talk, right?
Yes, tomorrow is another talk.
What time is the talk?
12 noon at the Boston time.
Thanks, Subir.
12 noon.
Okay, bye, Andre. Bye, Chandra. Bye, Ilya. And bye, everybody.
Hi, 诸位。